Hey there, 1100. We are doing standing waves on a string today. Now, this is going to be a quick one, but before you watch this, read your lab manual, understand what you're supposed to be doing, because I'm not going to talk about theory at all. I am just going to be a set of hands for you. And also, this is going to be a relatively quick lab, and that is because actually I already did it prior to filming this. I determined the amounts of weights that we're going to need to put on the end of the string to get the wavelengths of interest. Now that's pretty time consuming, so I did it off camera, and that's what takes, most of the time spent in the lab would be you figuring out what weights to use. So that's already done, and I'll just show you what we've come up with. This particular lab presents certain challenges in the way of filming. Right now you're mounted up above me so that you could kind of see what I'm working with. This is this white board that I have our oscillator hooked up to. One end is our oscillator, the other end is a pulley. You can't see it right now. We are going to get this string vibrating and produce some standing waves. So that's why you're mounted up there, so you can get somewhat of a view of this whole thing. Although during the experiment, you're not going to see the whole thing. I mean, I could mount you so high up that this whole thing is in view, but it defeats the purpose. You won't be able to see the details of what's going on here. So I will zoom in on it or mount you closer to the string so that you'll only see a portion of it, but I'll just play that by ear. Let me put you on pause and give you a close-up of the individual components. So hold on. Okay, what you're looking at now is our oscillator. These are nothing more than just clamps connecting it to the bench here, and this oscillates back and forth, producing our waves. We have a string which runs across the length of our table. It's loose right now because there's no weight on it, but it will ultimately be straight. And this is our pulley. Our hook will be on the other end of that pulley, and we could adjust the tension in that string by simply placing weights on that hook there. So let's get started. I'll put you on pause. Okay, actually before we get started, let's make an important measurement. And actually before we do that, let's talk about nodes for a second. For the duration of this experiment, throughout the course of our different wavelengths that we obtain, there are going to be two nodes that are always in the same position. The first one will be at the location of the pulley. In other words, right here, right where the string touches the pulley, that part of the string is never going to move, right? It's stationary, so by definition, it is a node. And the other node that will always be at the same location is, well, I'm not going to move this bench because it's way over there. It is at the location of the oscillator. So there is a little arm on that vibrator, and it moves back and forth. The string is attached to it, and it produces the waves on the string. Now, the node isn't going to be at the tip of that vibrator. As you can see when I'm moving the screwdriver, the tip right there isn't stationary, right? Well, of course it's not. If it was, it wouldn't produce a wave. The node, we are going to approximate it somewhat behind the arm, somewhere around here. So that's going to introduce a little bit of error in our measurement, but not much at all, because the length of the string is so large compared with that uncertainty in distance. Now, I have this 2-meter stick, and what I want to do is measure the length of our string from those two nodes. After all, for our first data point, we are going to get only one loop, and that one loop has exactly two nodes. Where are those nodes? Well, one is at the vibrator, the other is at the pulley. Now, let's see what distance that is. I'm measuring this here, and the distance between those two nodes is 175.5 centimeters. 175.5 centimeters. So that is our L, our capital L, as defined in your lab manual. It's always the same throughout the experiment. So I'll put you on pause and let's get this thing shaken. So we have our first standing wave set up, and I'll give you a better view of that momentarily. What I wanted to bring to your attention was the node near that oscillator there. So see the arm, and forgive me if I'm shaking, I'm holding the camera. There's the arm, and you could see that we can't necessarily measure from the tip of this. That isn't truly where the node is. And of course it couldn't be because the string is moving at that particular point. The node, I'm approximating it at about this location right there. So that's where I measured, that's where I began the measurement of our L. So let me put you on pause and give you a better shot of this standing wave. So there's like a whole view of the standing wave. You could see both nodes. Well, you know what? That node way out there, the pulley, you probably can't see, but there is our first standing wave. Let me put you on pause and show you the effect of resonance. Now, your lab manual talked about the phenomena of resonance. Resonance occurs when the nodes are at those two particular points that I mentioned before, one at the pulley and one at the vibrating arm. When they are located in that position, we will get large amplitude. Now, that helps us pinpoint when we have the correct wavelength, or when we have the nodes at the correct location. So what I'm going to do is like lighten the tension in the string just a little bit. So I'm doing it with my hand. And you see that the amplitude gets smaller. So now what I'll do is I'll increase the tension and it gets smaller as well. Actually, when I lighten it up a little bit, it's getting a little bit larger. So what that tells me is that I have too much weight on this hook. I should probably get rid of some. I'll put you on pause and I will find the precise amount of weight that I need. So, ladies and gentlemen, this is by far my worst video, and no fault of my own. It's just not conducive to putting on video. So we have our first loop. Our n is equal to 1. There it is. And how much weight do we have on the end of this string? It is 600 grams. So that is our first data point. Now let me adjust the weight and see if we can get 2 loops. I already have, I found out what weight is required, fine-tuned it, and I'll put that on the other end now and see what we get. So of course you can't see the whole thing. Let me take a peek at what you're looking at, but indeed we have 2 loops. 1 node there, 1 node on that end, and 1 node dead center. 2 loops. How much weight is on the end of that string? It is 155 grams. That is your second data point. The good thing about this video is it's going to be short. Now for the 3 loops. There you go. 1 node there, 1 node there, 1 node there, and the other node right there. So that is 3 loops, and the weight on the end of that string is 68 grams. And the weight on the end of this string, the hook is like kind of swinging back and forth. That's why these standing waves seem to be rotating. But anyway, there you go. For 3 loops, we have 68 grams. Now, we are shooting for 4 loops. Let me get these weights on this hook here. I had to switch over to a lighter hook. The more nodes we get, the less weight we need to put on the end of that string. So there we go. 1, 2, 3, 4. 4 loops. So 4 loops, we were able to produce that standing wave with 39.1 grams. Okay, so here is our 5 loops, and I am going to actually change the view on, well, I'll reposition the camera, so let me put you on pause. So this isn't much of a better view, but there you go. There's a node here and a node there. As our nodes or loops increase, you'll see that the amplitude of the standing wave gets smaller. So this was 1, 2, 3, 4, 5. So this is 5 loops, and for 5 loops, we put 25.1 grams on the end of that hook. Now let's go for some more. The more loops we get, well, as we go up a number, the harder they are to find. So here is our next one. So we are skipping 7. This is 7 loops. 7. 1, 2, 3, 4, 5, 6. Okay, 7. And to get those, 13.1 grams. 13.1. These were very hard to find. I couldn't seem to find 6, so I skipped it with no loss, because we are getting more data points than are required anyway. And this is the last one we're getting. This has 8 loops. Now, the amount of weight is very small on the end of this string. In fact, there are a bunch of 1 gram weights. They're really thin wafers, and they're stacked on top of each other, and they're vibrating. And because they're vibrating, this standing wave, it's like it's rotating. So it appears as if the amplitude is getting larger and smaller, larger and smaller. It really isn't. It's just that it's actually rotating. And our 8 loops was obtained by putting 9.27 grams on the end of that string. Actually, it kind of stabilized right now. I don't know if you can see it. Well, now it started rotating again. But anyway, there you go. Those are our, 1, 2, 3, 4, 5, 6. Those are our 7 data points. I'll put you on pause. I want to show you something. Hold on. Okay. All right, ladies and gentlemen, what you are looking at right now is a standing wave. And see that string right there? It may appear as if it is not moving, but it is indeed moving at 60 hertz or 60 times per second. And I'll convince you of that in a second. What you're looking at right now is a strobe light, and that's the frequency of the strobe light. Now I'm going to adjust the frequency just a bit. So as I adjust the frequency, you could see it move. drastically decrease it. Okay, now that's really messing up the camera. But there you go. Let me put you on pause and put it on a different finely tuned frequency. Hold on. Okay, so I had the strobe light on that standing wave at 3,600 RPMs. So that is 3,600 flashes per minute, which converts to 60 per second. Can we conclusively say that our string was vibrating at the same frequency, 60 per second? No. I was going to put this on a different frequency for you and prove that point, but the camera wasn't picking it up. It was getting all messed up, so I just didn't do it. In other words, I could have tuned this to 1800 RPMs and still have produced an image that seems stationary. So that's a hint. Of course, I could systematically verify the frequency of our waves by adjusting this, but I won't go into that, let you figure it out. Let's see. Oh, the last thing is, hold on for a second. You need to determine the linear density of our string. Now, there's going to be error associated with this beyond our ability to accurately measure it. And that is because the linear density is technically going to change over the course of this experiment. Well, how? We're using the same string. Well, here's the catch. We're using different tensions on that string. To get n is equal to 1, to get one loop, we hung a lot of weight, over 600 grams, right? Well, actually 600 grams exactly. And the lowest tension we put on was a little less than 10. The string stretches over that span of weight up to 2 centimeters. So the linear density changes. And of course, linear density is nothing more than mass per unit length. So you can see that it's going to fluctuate a bit. But anyway, I cut a large portion of that string and weighed it. The portion of the string I cut measured 170 centimeters. So I got 170 centimeter length of that string, weighed it, and it came out to 0.24 grams. Fortunately, I couldn't calibrate my digital scale, so we're going to trust it. But I guess I'm saying this because if you get some relatively large error, it could be a result of the scale. That string is so light. I wish I had a more sensitive and accurate scale here. But anyway, there you go. And I apologize for the quality of this video. I mean, you really couldn't see or appreciate what was going on. It's unfortunate. This is our last one together, but maybe I'll see you next semester in 1200. We are done. I won't see you next week, but good luck.